Oh,
Yeah,
the
yeah.
is it still operational? I heard that
It is
they.
cleanup. Like you can go on tours of the cleanup
Oh,
with
okay.
the engineers and the people who ran it.
Oh, that's
So you
really
do
cool.
tours on weekend.
Oh, that's really cool.
Yeah, I didn't know that. And then one of my senior design mates, they said, "Oh yeah, I went with my boyfriend."
Uh-huh.
And I'm like, "You did what?"
Yeah, I mean, I know they shut it down a while ago, but it makes sense that they're still working on the cleanup there.
I'm like, "Okay, cool, I'll do that."
Mhm.
So, so I sent an email. Hopefully, I get a good response
Nice.
that I can set it up for next semester because they're already full till August.
Oh, wow.
So they're already booked out. So I was gonna send one for September of next year,
Makes
of this
sense.
year.
Yeah, that'd be really cool.
Oh, you might also need to know this. You will need to know this.
Mhm.
There's a chance, fairly high chance, we're gonna be hosting the picnic again.
Okay.
So in April.
Okay.
So we'll need to figure out all the bookings.
Got it. Is it just because we have free parking on the weekend?
Uh, no, it's just we're most centrally located.
Oh, I see. Okay. I see. Okay.
And Dr. and Mr. Sam likes our chapter like usual. So
Oh yeah. I mean, he graduated from here, so
yeah, so it's like, hey, you guys do it. And it's like, okay, cool. I guess we don't have the the green space anymore. It's a construction yard.
oh yeah, that's true. Well, I mean, so I think last year the picnic fell on the same day as the like welcome new student day. So the green space was unavailable that day too. But I don't know what they're going to do with the welcome to Cal State Fullerton day, or they called them something weird, like become a Titan or something like that.
Yeah, well, he could have the convention on Saturday, on
Mm.
Monday. So it's still up in the air. We're still talking with like Neil and everyone.
Okay, sounds good. Yeah, let me know.
Okay, yeah, we need to work for it.
Mhm. All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good to hear. All right, so it's week 6, and so I know this is kind of when the semester really starts to pick up. So midterms are going to occur over the next couple of weeks. So I did want to let you guys know when our midterm is going to be. So our midterm is going to be on Monday, March 9th. So that is 2 weeks from today. The topics that are covered on the midterm, you can expect the first 3 homeworks to be on the midterm. So that's homework 1, homework 2, and the newly posted homework 3. Homework 3 was posted today, just about an hour ago. That's when I finished it. And that is due Wednesday, March 4th. So that is next Wednesday. Okay. So things are going to pick up a little bit in this class. It's going to be a busy next couple of weeks, but it's probably going to be busy next couple of weeks in all of your classes. So yeah, I just wanted to make you guys aware of those things. Okay. So in terms of format for the midterm exam, we'll probably go over it in more detail next week. But just at a glance, the midterm exam is going to have a very similar format as the homework. So you can expect there to be conceptual short answer questions that'll make up about 40% of the points. And then there will be problem solving questions where, all we've kind of done up to this point is just deriving finite difference and finite volume type of equations. Okay. So first thing I always tell people is that, do the homeworks, study the homeworks, because that's very much going to be very similar to what's going to be on the exam. I write the homeworks myself. I write the exams too. And so, they're going to be exactly the same style. For the midterm exam, you're also allowed to bring a single 8.5 by 11 sheet of notes. You can use front and back. You can type it, you can write it, whatever you want. So definitely make use of that, to put whatever you want to help you with the exam as well. Okay. And then besides that, you can bring a writing utensil and a calculator, bottle of water if you need to. You don't need the water for the exam. The water is just for your own personal survival. But that's what you can expect. Okay. So the exam will take place in class on Monday, March 9th. And so, we won't have lecture that day, but you do need to be here, obviously, to take the exam. Okay. All right. So the plan for today is we're going to continue with our lecture on 2D finite volumes. And so we're going to be doing diffusion equation. And then over the next 2 lectures, we'll be doing convection and finite volumes. So I'm hoping that the last lecture that will be covered on the midterm exam will be next Monday. So we have 3 more lectures to go for the content for this midterm exam. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started. Okay. So topic for today is 2D diffusion with finite volumes. Okay. So last time we were here, last Wednesday, we applied the finite volume technique to our very first equation, which was 1D diffusion. And we kind of went through the entire process with that in terms of starting with the differential equation, integrating it, applying divergence theorem, and then getting our equations, right? And so we saw that the biggest difference, right? The biggest difference between finite volumes and finite differences I wrote out finite differences and I got lazy, so I said the next one can just be f of e for finite volumes, right? So the biggest difference is how we apply the boundary conditions. Okay. So that was kind of a big point of emphasis from the lecture last Wednesday. So, if you recall from finite differences, right? In finite differences, the way that we apply the boundary condition was that the boundary conditions kind of became their own equation because we had the finite difference nodes that were sitting directly on the boundary. right? So we had nodes that were directly sitting on the Dirichlet boundary condition. And so we can say that the value of the solution at that node directly equals the boundary condition. And then we could do the same thing with Neumann boundary conditions, right? Whereas for finite volumes, right, the big change that we saw last week was that boundary conditions don't become their own equation, but they modify the general finite volume equations that we have for that particular scenario. Okay. Right. So remember the way that we kind of presented finite volumes was that we derived a general finite volume equation for an interior cell. Remember, an interior cell is one that has neighbors on all sides. And then we learned how to modify these equations, according to the boundary conditions if our cell borders the boundary. Okay. So we're going to take that same approach today. And so today we're going to, we're going to look at 2D diffusion. We're going to derive a general finite volume equation that is, that has to do with, assuming we have neighbors on all sides, and then we'll go over how to modify those equations according to the boundary conditions. Okay. Okay. We're also going to see a little bit more of the integral rules that we kind of hinted at early last week on Monday. So you actually get to see divergence theorem and kind of all of its glory today in terms of simplifying our integrals. Okay. All right, so that's kind of where we're going, and that's kind of just a recap of where we were last time. Just any questions on this? Okay. All right, so let's go ahead and get started then. So let me go ahead and draw. Let's start with a generic finite volume cell in 2D. Okay. All right, so our cell is a simple square, just like that. Okay. And so just like we saw in 1D, we're going to solve for the solution values at the center of the cell. Okay. So I like to use this notation. So I like to use phi sub c, where c stands for center. Okay, so this is our center cell. And then we have all of its neighbors. Okay. Right, so we have our neighbor to the north. Okay. So that's phi sub capital N. We have its neighbor to the east. Okay, so that's phi sub E. We have our neighbor to the south, and so that's phi sub S. And then we have our neighbor to the west, and that's phi sub W. Okay. Okay. So the reason I bring up all the neighbors is because they're all going to be participating in the finite volume equation, just like in finite differences. Okay. Now, one notational thing that I use here is that if you notice, all the self-centered values here have capital letters for their subscripts. Okay. So I write that out explicitly just because, for some letters like E and N, it's very obvious which is, uppercase and lowercase. But for some of the other ones like W and S, the uppercase and lowercase W and S they look the same, it's just one's bigger than the other. But when you're kind of writing it on the board like this, it sometimes it's kind of hard to tell. But just for your own notes and for your own notation, just know that self-centered values always use capital letters. Okay. Okay. We're going to bring in lowercase letters too, but then, we'll kind of introduce that once we kind of get there. Okay. Okay. So once again, let's start with our 2D diffusion equation, and then let's apply the finite volume method to derive the equation. Okay. Okay. So our 2D diffusion equation is the following. And so just like before, I'm going to write it in vector notation. We have K multiplied by the divergence of the gradient of phi is equal to q of x and y, okay? Or the term on the left-hand side of the equal sign, that's our diffusion term, and the term on the right, the q, that is our source term, okay? Now, just like we did before, we're going to integrate this, but instead of a single integral, we're now doing a double integral because we have to cover the entire area of our cell. Okay? So we're going to do a double integral across the area of the cell, okay? And then same thing on the left-hand side. Okay. All right, so we're only integrating these equations across our center cell, right? So, even though the neighbors are there, the neighbors will come in soon, but, we're only integrating this on our central cell right here, okay? So for a square, that's fairly straightforward. We're just integrating from, in x and then in y. But, we'll keep the integrals generic here just so that, we can apply this for an arbitrarily shaped cell. Okay. Okay. All right, so let's go ahead and evaluate these integrals. So first thing we're going to do is we're going to work on the left-hand side. Okay. Because this integral that we have on the left-hand side fits perfectly into our divergence theorem. Okay, so we're going to use divergence theorem. Okay. Remember, divergence theorem is the mathematical tool that we can use to convert integrals from one form to another. Okay. Because right now we have the integral, a 2D integral over an area of the divergence of the gradient. Okay. To say that slow just because it's a mouthful. But we want to use divergence theorem here to essentially remove the divergence, right? Just one less derivative operator to deal with in the middle. But then that also changes the nature of our integral here. So we're going to use divergence theorem to convert this to a line integral around the exterior of our cell. Okay. Okay, so we do that, and then we end up with the following. So we end up with, well, first of all, I'm going to take k. So k is just a constant. We're going to assume that we could just have constant k. We're going to pull that out of the integral. Okay. So we have k multiplied by line integral around the boundary of A, right? So we have that, I use that partial A notation to denote that this is going around the boundary of our cell, okay? Of the gradient of phi dot product with the normal vector, okay? ds. Okay. And then on the right-hand side, we're going to do just the same thing that we did before. So we're just going to directly apply trapezoidal rule for this, and then evaluate that using our 1-point trapezoidal rule, okay? So this is going to be q at x sub c, y sub c, okay? So this q at x sub c, y sub c, this is our source term evaluated at the centroid of the cell. Okay. And then we're going to multiply by the area of the cell, which is just delta x, delta y. Right, so that right-hand side, that's simply just our trapezoidal rule applied to our source integral, okay? So that one we're done with, so we're not going to worry about the right-hand side anymore. That's pretty much a done deal. But we're going to spend the majority of today working on the left-hand side of this expression. Okay. Okay. All right, any questions on this so far? Okay. All right, so let's look and see what this looks like here. So this integral here, right? This line integral essentially means that we're basically going to be following a path around the exterior of our cell. So let me go ahead and draw the cell one more time. Okay. I'm going to focus just on the center of the cell, or just on the central cell. Okay. Right. And so this line integral essentially means that we're going to be following a path around the outside, right? And so we're going to be going like this. You don't have to start from the lower left-hand corner. I mean, essentially, we're going to be tracing a closed path, and so it doesn't really matter where you start. Um, it's just that's just kind of where I like to start. Okay, so maybe a little bit refresher of maybe Calc 3, maybe some 308. You might have covered this in 308 as well, right? So when you have a line integral, you're basically tracing a path in two-dimensional space. So line integrals are interesting. So it's technically a one-dimensional integral, so we're only integrating along a path, but that path can exist in 2D or 3D space. All right, so I'm going to do this as well. So, because our path here has some sharp turns, right? So, our path has to it goes along an edge, it reaches a corner, and then it has to make a sharp turn. Kind of the best way to actually approach this is to actually break up that line integral into 4 different components, just because it's hard to kind of parameterize that sharp turn. And so I'm going to call the bottom face here, we'll call this face S. Okay. The right-hand side, we'll call that face E or edge E. The top edge, we'll call that N. And the left-hand side, we'll call W. Okay, so the same compass directions, but you can see we're using lowercase letters. Okay. So whenever you see lowercase, indicators or lowercase labels, that refers to quantities evaluated at the face of the cell. Okay. So uppercase self-center, lowercase face. Okay. And then on each of these faces here, we're going to draw an outward unit normal. Okay. All right. So an outward unit normal is basically just a unit vector that points in the direction normal to that face. Okay. Right. And you can see for each of the faces here, the normal vector points in a different direction, just because outward is different for each of those faces. Okay. That's kind of another reason we break this up, just because the normal vector changes the face. Okay. Okay. So with this diagram in mind, let's go ahead and break up our line integral into each of the 4 faces. Okay, so we're going to have one line integral for each face here. Okay. All right, so we're going to basically take this K line integral on a closed surface, partial A of gradient of phi dot product of n ds. Okay. We're going to break this up into 4 line integrals, one for each edge or one for each face of our cell. Okay. All right, so we're going to have an integral on the east face of gradient of phi dot n hat ds. Okay. And then remember, with integrals, as long as you're kind of staying on the same path, right, we can just simply add them together, right? So the integral on the east side is going to be added to the integral on the north side. Okay. To this, we're going to add the integral on the west side. And then to that, we're going to add the integral on the south side. Okay. All right, so doing this, avoids us having the issue where, our normal vector changes along the path, but along each edge, right? So along the entire south edge or the entire east edge, our normal vector is constant, right? So we don't have to worry about that changing. It's going to afford another kind of simplification for us as well, because, the gradient of phi also has, distinct values on each edge as well. Okay, it just kind of makes our lives simple. I know it kind of seems like we're making it more complicated by taking one integral and turning into four. But it does actually make our lives easier because we can evaluate each of these individually and then just add them all up at the end. Okay. Okay. All right. So now that we've kind of broken up our line integral here, let's evaluate the integrand and see what that looks like for each of these things. Okay. So if you look at all the integrands are the same. So we're taking the dot product between the gradient of phi and the normal unit vector. Okay. Okay, so let's examine that and see what that looks like. So first we have the gradient of phi, right? So like I mentioned, I think maybe not last class, but I think the class before that, when you take the gradient of a field, you essentially get a vector out of it because the gradient is essentially going to be the partial derivative of that field in every possible direction. Okay, so the gradient of phi here, this is a vector, right? So the x component of that vector is going to be partial phi partial x, right? And the y component is partial phi partial y. Right. And if we were in 3 dimensions, then our gradient would have 3 components. We'd also have a partial z component. But since we're in 2D, we can just stick to just these 2 components. Okay. Okay. So that's the first thing. Okay. Now let's quantify the normal vector for each face. Okay. All right. So like I said, the normal vector is going to have a different value on each of the faces here. So let's write out what their value is on the east face. We'll write the value on the north face, on the west face, and the south face. Okay. Okay. So remember, the outward unit normal is a vector with length 1, and it points in the direction of the outward normal. Okay, so let's go back up to our figure here. Okay. And so if we look at the east face, right? The east face is a vertical face that kind of goes up and down, right? Right. So a direction normal to that would be pointing directly to the right, right? And so we can quantify this, right? So knowing the fact that the normal vector has to have length 1, and we know for the fact it's pointing basically directly east, it's pointing right at 3 o'clock, right? That means one expression for the normal vector, or actually the only expression for the normal vector, is 1, 0. Okay. So let's write that into our table here, right? So on the east face, our normal vector will have the value of 1, 0. Right? And we can do the exact same thing for all the other faces using that exact same logic. Just knowing that the normal vector has to have length 1, and it points in the direction normal to that face. Okay. So for the north side, the normal vector has a value of 0, 1, right? Because it's pointing vertically upwards. On the west face, our normal vector is pointing to the left, right? And so that has a value of -1, 0. And then on the south face, we have our outward unit normal is pointing directly down. And so that has a value of 0, -1. Right. All right, so now that we know what the gradient vector looks like, now that we know what the outward unit normal looks like for each of the faces, we can then easily just compute their dot products. And you can see that it's going to be different for every single face. And so that's part of the reason why we kind of split up that line integral into 4 different components. Okay? But before we kind of do those dot products, are there any questions on how we got these kind of results here? Yeah.
Question. So if you have bigger grid spaces, will those values change?
It's a good question. So this cell that I drew here was kind of independent of size. And so we haven't made any kind of reference to any kind of grid spacing yet. It's going to come in very soon. And so these expressions here, right, for now are independent of the grid spacing. What you're going to see now, what you're going to see soon, though, is that when we evaluate these integrals, those will depend on the grid space. But up until this point, we've made no reference to that yet. Yeah. Okay. All right. So let's go ahead and evaluate that dot product for each face. By the way, I call them faces just because I'm used to kind of the 3D theory. So if you have a 3D cell, then the outward components are faces. But I realize in 2D it's not really a face, it's an edge. But I use faces just anyway. And the notation that's used in OpenFOAM, they say faces as well. So it's kind of good to get used to that kind of notation. Okay. Okay. So for the east face, right? So we have the dot product between the gradient vector and the unit normal, right? So we have 1 times partial phi partial x plus 0 times partial phi partial y, right? So that all that gives us is a positive partial phi partial x, okay? Which is good because then that eliminates kind of one component of the gradient. So we only have to worry about just the x derivative on the east face, okay? On the north face, same thing. And so, we have 0 times partial phi partial x plus 1 times partial phi partial y. All we're left with is partial phi partial y. Okay. Right. So the west and south faces are similar, but we do have to factor in that negative into account. So on the west face, we have a minus partial phi partial x. And on the south face, we have a minus partial phi partial. All right. Right, so now we're in business. So now we can take these and we can plug those into our line integral that we had above. Okay, so that gives us integral on the east face of just partial phi partial x ds, okay, plus integral on the north face of partial phi partial y ds, okay, minus integral on the west face partial phi partial x ds, minus integral on the south face of partial phi partial y ds. Okay. All right, so now that we have the integrals in this form, we're ready to evaluate them. Okay. We're not actually going to evaluate them. We're going to do our trapezoidal rule. Okay. Okay. So remember the way trapezoidal rule works. So if you have an integral, right, whether it be a 1D integral, 2D integral, right, the way trapezoidal rule works is that you evaluate the integrand at the centroid of your integration domain, and then you multiply that by the length of the domain. Okay. Since all of these are one-dimensional integrals, we're going to use the basically the 1D version of trapezoidal. Okay. Okay. And so that means, so I'm just going to scroll up to the figure one more time here. Okay. So let's say that we're evaluating the integral on the east face, right? So that means, let me use a color I haven't used yet. Use purple. Okay. So on this east face, right? When we evaluate the integral, we're going to evaluate it at the centroid of that line. Okay. So this purple dot here, this is the centroid of that east face. Okay. Right. So I know I'm using the word centroid here, but I'm not talking about the centroid of the cell, right? Since we're only integrating on that east face, we're just looking at the centroid of that east face. Okay. Okay. And so we're going to evaluate the integrand at that centroid there. And then we're going to multiply it by the length of that face, right? And so the length of the face here, so the length of the east side face is delta y, right? So delta y being the size of the cell in that direction. Okay. So this is where the grid spacing comes into play because now our integrals here are dependent on that grid spacing. Okay. All right. So if we do that, then that first integral then becomes partial phi partial x evaluated at the centroid of the east face. And so I'm just going to denote that with the lowercase e in the footnote. Okay. Multiplied by delta y. All right, and then we're going to do the same thing for the other integrals. So on the north face, we have partial phi partial y. Okay. And then we're evaluating that at the centroid of the north face. We're going to put a sub n, sub lowercase m. Okay. And then we're going to multiply by the length of that north face, which is delta x. Okay. Minus integral on the west face. And so that's going to be partial phi partial x evaluated at the centroid of the west face. So that's lowercase w. Multiplied by delta y. Minus partial phi partial y evaluate at the centroid of the south face, delta x. Okay, good. All right, so that's the left-hand side of our finite volume equation. Let me go ahead and write the right-hand side. Okay. So the right-hand side is our source term q of xc comma yc multiplied by delta x delta y. Okay. And then I'm going to go ahead and let's go ahead and box this equation. Okay. We're not done quite yet, right? And so obviously right now we don't have an algebraic equation just yet. But this equation here is good to keep in mind just because, when you are applying boundary conditions, this is always a good starting point when you're applying the boundary conditions. So this is our finite volume equation for 2D diffusion. Oh, by the way, I realized I forgot. We have our diffusion constant as well, right? So remember, we had a diffusion constant k that was multiplying the entire integral on the left-hand side. I'm going to go ahead and move that to the right. So I'm just going to divide both sides by it. So we're going to say this is going to be delta x, delta y on the right divided by k. That's usually where we put it anyway. We usually move it to the right-hand side. So, I just kind of did that step there. All right, good. Any questions on how we got this result here? All right, so that was a good exercise. So hopefully that kind of shows kind of how we use kind of a variety of different integral rules and integral kind of theorems there. Okay. Okay. Now, how do we actually turn this into an algebraic equation that we can use? Okay. So the way that we're going to do that is we're essentially going to take each of these derivatives here and apply a 1D finite difference rule to it. Okay. So basically, for all of these derivatives here, we're going to apply a simple central difference scheme for them. Okay. Right. So the location. So remember, each of those derivatives they're evaluated at the face of the cell, right? And so that location is actually very key. So I'm going to scroll up for just a second, right? Okay. So remember, this is our diagram. This is our stencil, right? So we have our central cell and we have all other neighbors, right? And so by applying the finite volume method, right? Essentially what we're saying is that in order for us to form our finite volume equations, we need to evaluate the derivative of the solution at each of those purple dots. Okay. So this purple dot here, this would be partial phi partial x, evaluate it at the east face, right? This is partial phi, partial y, evaluate at the north face, partial phi, partial y, value at the south face, and partial phi, partial x, value at the west face. Okay, a little bit of a mess, I know, but hopefully this was mostly just to illustrate kind of where these are. Okay, but hopefully you can see too that if we make a central difference scheme, we have two neighboring values, two neighboring self-centered values that we can use for their expression. Okay, so for instance, right, if we look at partial phi partial x on the east face, right? And since we're taking a derivative in the x direction, we need neighbors on the left and right. And it turns out that we do. So we have phi sub c, which is the central cell, and phi sub capital E, which is the east neighbor. Okay. Okay. So with that in mind, let's go ahead and apply those rules. Okay. So partial phi partial x at the east face. Okay. Using the neighboring self-centered values, this is partial or phi sub big E minus phi sub c, all divided by delta x. Okay. Right. So we looked at the two self-centered values that are neighboring this particular face, and we throw them into our central difference scheme. Okay. Right. And then we have partial phi, partial y at the north face. Okay. So this is equal to phi sub big N minus phi sub big C divided by delta y. Okay. Right. And then phi partial x on the west face is equal to phi sub big C minus phi sub big W delta x. Okay. And then very similar on the south face. Partial phi partial y. South face is equal to phi sub C minus phi sub S all over delta y. Okay. All right. So now we can take these and we can plug it into the expression above. Okay. Right. So let's do one more assumption, which is pretty reasonable most of the time, especially for this class. We can make the assumption that our grid spacing is going to be the same in the x and y directions. Okay, so for simplicity, let's assume delta x is equal to delta y. Okay. So up until this point, we haven't made any assumptions in terms of, the difference in the grid spacing. We kind of left them as different. But just because we're going to be plugging in and just to kind of make our life simpler, let's assume that they are the same. Okay. Okay, so what that allows us to do, right? So because if you look for the east integral, right? So we're plugging this guy here into right here. So we have phi sub E minus phi sub C divided by delta x multiplied by delta y. Okay. So if delta x and delta y are the same, we can just cancel them out. So we don't have to kind of worry about that expression at all. Okay, so we'll go ahead and plug that in, right? And of course, at this point, we've kind of assumed that we have an interior cell, right? So by forming all these expressions, right? So maybe I should have mentioned that earlier. We assume interior cell. So essentially, we have neighbors on all sides. Okay. Of course, if you don't have a neighbor on this particular side, so let's say that your cell borders a boundary, we're going to have to modify this. But we'll go over that kind of in the next thing. Okay. Okay. But just with this, let's go ahead and plug in, right? And so our first expression, so so what you can see, all the delta x and delta y's on the left-hand side are all going to cancel out essentially. Okay. And so all that we have left is partial phi, phi sub big E minus phi sub C plus phi sub big N minus phi sub C, okay, minus phi sub C minus phi sub W minus phi sub C minus phi sub S, okay. And all this is equal to Q at XC comma YC delta squared divided by K. Okay. So of course we can simplify this. And so we have a bunch of phi sub C terms on the left-hand side. So let's go ahead and combine them together. Okay. And then after we combine, you'll see that we'll finally get the expression for our finite volume equation for an interior cell, considering just 2D diffusion. Okay, so we simplify the left-hand side. What we get is phi sub E plus phi sub N plus phi sub W plus phi sub S minus 4 phi sub C is equal to Q at XC comma YC delta squared divided by K. Okay, so this is our finite volume equation for an interior cell for a 2D diffusion equation. Okay, so again, this assumes that we have neighbors on both sides. Okay. Right. So let me put a word of caution right now. So we're going to be boxing a lot of these equations, but you want to be really careful when you're just plugging and chugging, because each of these equations that we have here have a very specific use case, right? So for this particular equation, right, this is for specifically an interior cell. So I don't mind if you just kind of use these equations as they are, on your homework, granted that you know exactly what situation you're using them for. But it is still very useful to kind of understand the details of the derivation. And you're going to see why very quickly, because once boundary conditions start to become a factor, then you really want to know the procedure and the process so that you can modify it according to where your boundary condition is. Okay. And then once we add convection into the whole thing, once we start talking about it on Wednesday, then it gets really, really complicated. So there's a lot of different rules with convection in terms of upwinding, non-upwinding, what you do with the boundary conditions and okay. So again, I don't mind you using just these equations, but just make sure that you know exactly what situation that you're using it in. Okay. Okay. All right. Any questions on how we got to this point here? Okay. All right, so first thing you should notice is that the left-hand side looks very similar, right? So if you go back to your notes on 2D diffusion and finite differences, we have that exact same pattern. So 1, 1, 1, 1, minus 4, where each of our neighbors has a weight of 1, and then our central cell has minus 4, right? So this kind of follows the same trend where, when we did 1D diffusion last Wednesday, we had the same kind of stencil pattern. Here. So that's kind of the same. So it's kind of reassuring, but also at the same time we spent 45 minutes going through this whole derivation to essentially get the same result, right? Okay. So that kind of goes back to the first thing I said today, where finite difference, finite volume, at least for the interior cells, the equations look very, very similar. But where they do really differ is how you actually apply the conditions. Okay. So let's get to that. So let's go ahead and learn how we can apply our boundary conditions. So let's do Dirichlet BC in 2D diffusion. Okay. So remember, when you're doing finite volume methods here, right, we know that the boundary conditions are going to modify our equation. Okay. So for cells that border a Dirichlet boundary condition, we are going to get an expression like the one we have boxed here. It's just that the coefficients are going to be slightly different because of the Dirichlet boundary condition. Okay. All right, and then one other kind of caution to note here. So same thing I said last Wednesday, that where the boundary condition is applied, right? Whether it's on the east side, the north side, west, or south, that is going to affect the value and how that actually affects your coefficients, right? So just like in the 1D case, I'm going to illustrate to you kind of the process on how to derive a case with the boundary condition, right? We don't have enough time to go over every single case, and so we're not gonna have a boxed equation for, what happens if the derivative boundary condition is on the south versus on the west versus on the east versus the north, right? What if you have a situation where you have two boundaries as a derivative boundary condition, right? So there's too many scenarios to kind of cover and get box equations for those, but so for these parts, it's important that you know the process of how we get. Okay. Okay, so with that said, let's look at a specific case, just for the sake of of being able to write an equation. So let's look at a case where we have a Dirichlet boundary condition on the west face. Okay. Okay, so in other words, we have a situation like this. So let's say we have our center cell, just like we normally do. Okay, so that's phi sub c. Then we have its neighbors. And so, we're not going to have a neighbor on the west, right? Because we have a Dirichlet boundary condition there. But we are going to have a neighbors to the north. We're going to have a neighbor to the east and a neighbor to the south. Okay. And then on the west face, we are going to have our Dirichlet boundary condition there. So we're going to say phi is equal to phi sub naught. Okay. So the way to tackle these situations is to, first of all, kind of make note in terms of where the boundary condition is applied. Okay. And then also just to kind of realize that, that Dirichlet boundary condition is only going to affect your boundary integral or your line integral on that face alone. Okay. So boundary conditions only affect the line integral on the faces that it borders. Okay. Right. So for all other line integrals, for all other integrals where we have a neighbor on that side, those will be unaffected. Okay. All right. So for this particular case here, right, we have neighbors on the north, east, and south side. So that means those three line integrals are going to have the exact same values as before. Okay. All right. So that means, you can go back to, how we derived our interior cell equation. Okay. And you can just write in those exact values there, right? And so that's kind of the reason why I broke it up like this. So, if we look at this expression here, before we simplified, all right, this contribution here came from the east integral. This contribution here came from the north integral. This one came from the west. And this one came from the south, right? Okay. Right, so knowing that for our particular example, the east, north, and south integrals are the same, right? We can just take these parts here and just plug them back down here. Okay? So the only one that's going to change is the west integral. Okay, so with that in mind, let's go ahead and write those in. Okay? So for the east integral, right, we do everything. We end up with the contribution of phi sub e minus phi sub c. For the north integral, this is also unchanged, phi sub n minus phi sub c. Okay. And then on the south, right, we have phi sub c minus phi sub s. Okay. So these are contributions from those integrals. Okay, so we're gonna add those to our result at the end. Okay. So the only one that changes here is the West. And so for the West integral, right, we do our entire kind of thing. We do our, our divergence theorem. We do our trapezoidal rule. What we end up with is partial phi, partial x, evaluate at the West face, multiplied by delta y. Okay. And there's a minus sign technically here. Okay? And there's a minus sign for the South contributions too. Okay. All right, so let's evaluate this derivative using finite differences with that Dirichlet boundary condition in mind. Okay, so just like we did in the 1D case, we're going to do kind of like a half step, right? So we take a half step from the center of the cell to the boundary, okay? And we use that to compute our derivative. All right, so we have a minus. Okay. We're going to take phi sub c minus phi sub naught, okay? Right, so that's the difference between our cell-centered value and our given Dirichlet value. And since we only took a half step, right? So the distance between the center of the cell and the boundary is delta x divided by 2. Okay. We're going to divide this by delta x divided by 2. Okay. We sub delta y. All right, so let's go ahead and simplify this. And so if we simplify, we bring the negative inside, we take the 1/2 up top, we cancel out delta x, delta y, right? So we're still going to make the assumption that our grid spacing is uniform, okay? We end up with a positive 2 times phi naught minus 2 times phi sub c. Okay. Okay. So let's take this and add it to our 3 others above. Question, yes.
Delta x and delta y. Assumption.
Exactly. Yeah. So we're still making the assumption that delta x, delta y are the same. Yeah. Okay. So remember, this is the assumption of essentially a uniform grid. And being weird, right? Another way you can say is that our cells are perfectly square, so they're same edge size vertically. Okay, so let's go ahead and add all these together. Okay. So we have phi sub e minus phi sub c. That's the contribution from the east integral, plus phi sub n minus phi sub c. That's the contribution from the north integral. Okay. Minus phi sub c minus phi sub s. That's the contribution from the south integral. And then we have the contribution from the Dirichlet boundary condition, which is a plus 2 phi naught minus 2 phi sub c. Okay. And all this is equal to q at xc comma yc delta squared, all divided by k. All right, and so from here, all we have to do is just simplify because we have a bunch of common terms on the left, okay? The other thing that we'll do is, we'll make note that this phi naught, remember, is known, right? Because you often know your Dirichlet boundary, well, you have to know your Dirichlet boundary conditions before you start. And so since it's a known quantity, we're going to move it to the right-hand side. Okay. And so if we simplify, we get the following. So we get phi sub e plus phi sub n plus phi sub s minus, okay. We count the contributions to phi sub c. We see we get a minus 5. Phi sub c is equal to q at xc comma yc delta squared over k minus 2 phi naught. Okay, and so that is our finite volume expression for that Dirichlet. All right. So let's look at the differences, right? And so first thing we notice on the left-hand side, we don't have any contribution from phi sub w, right? That makes sense. We don't have a neighbor on the west side, so we shouldn't have any contribution from there. Okay. And then our contribution to our central cell, right? Now we have a coefficient of -5 here as opposed to -4 for our interior cell. Okay. And of course, the other obvious thing is that our Dirichlet boundary condition gets moved to the right-hand side. Okay. Any questions on how we got this result here? Okay. So remember, this whole procedure, or I would say, the procedure doesn't change, but your result does change, if you have the Dirichlet boundary condition, let's say you have it on the east, unless you have the Dirichlet boundary condition on the south or the north, right? And so, it's important to kind of know this procedure. It's not that long, right? So I was able to fit it all on one screen here, right? And so the important thing to remember is that, for the edges or for the faces that don't have a boundary condition, those contributions stay the same, right? And so you don't have to reevaluate those integrals. You can just go based on what you know before, right? So the only integrals that you do have to change are the ones that border the boundary. Okay. Okay. So in this case, the only integral that we modified was the west integral because that's where the Dirichlet boundary is. Okay, so let's do the same process, but now let's do a Neumann boundary condition. So this one actually is a little bit simpler. Okay. So remember, Neumann boundary conditions, these are boundary conditions on the derivative of the solution at the boundary. Okay. So that actually makes things quite simple to evaluate because remember, each of our face integrals here is basically the integral on a derivative, right? And so we basically just replace that derivative with our Neumann value. We don't even have to do finite differences. Okay. Okay, so like I said, the exact expression that you get changes depending on where the Neumann boundary condition is, right? So whether it's on the south, east, north, west, right? So I'm not going to do every single situation, but I am going to do one just so that you can kind of see how it is. So let's do a situation where our Neumann boundary condition is on the south. Okay. All right, so our situation looks like the following. So we have our center cell here. And we have all of its neighbors. Okay. Okay. So since our boundary condition is only on the south, we still have neighbors to the east and the west and the north. Okay. And then on the south side, we have partial phi partial n is equal to gamma. Okay. Where gamma, that's the numerical value of our Neumann boundary condition. Okay. Okay. So here we're going to make the same observation we did for the last example, right? And so we note that the integrals on the east, the west, and the north faces are all exactly the same. Okay. So we can go ahead and write their contributions here, okay? And again, these expressions assume a uniform grid spacing. So on the north, right, our contribution for that is phi sub n minus phi sub c. On the east, our contribution from that one is phi sub e minus phi sub c. And on the west, we have a minus phi sub c minus phi sub w. Okay. All right, so those are not going to change. That's 3 out of 4 of the integrals that we already kind of know the expression for. Okay. Now on the south, we have the integral of partial phi, partial y on the south, ds. Okay. Which, if we evaluate at the centroid, we use trapezoidal rule as just partial phi, partial y, minus sign, right? So the minus sign comes from the normal vector. I forgot to put that. Okay. Multiplied by delta x. Okay. Okay. So remember, for Neumann boundary conditions and finite volumes, it's pretty straightforward because all we have to do, right? Since we're evaluating the derivative, or what we want to evaluate is the derivative on that face anyway, let's just take our Neumann value and then plug it straight into here. So we don't even have to do any central differencing, okay? So that means the contribution from the south integral is minus gamma delta x. All right. Good. So now we have all 4 of our integrals evaluated. Our right-hand side sourcing term, that always kind of stays the same. So now all we have to do now is just kind of add all these together and then form our finite volume equation. Okay. All right, so let's go ahead and add all these contributions. So we have the north contribution, so that's phi sub n minus phi sub c, okay, plus phi sub e minus phi sub c. That's the contribution from the east integral. From the west integral, we have a minus phi sub c minus phi sub w. Okay. And then from the south integral, we have a minus gamma delta x. Okay. Technically, it's delta, right? So we're assuming that delta x, delta y are the same, but just so you know kind of where it comes from. And on the right-hand side, we have q at xc comma yc delta squared divided by k. All right, so then all we have left to do now is we just have to simplify this, okay? And let's note the fact that our Neumann term, the term with the gamma, remember that is always new. So we can go ahead and move that to the right-hand side. Okay, so let's go ahead and move it over there. And then all we're left with here is phi sub n plus phi sub e plus phi sub w minus, we're going to add all the contributions to phi sub c. We can see that we have a minus 3 phi sub c is equal to q at xc comma yc delta squared divided by k plus gamma delta x. Right, so this is the finite volume equation that we get for the case when we have a Neumann boundary condition on the south side of our cell. Okay. All right, any questions on this example here? Okay, good. All right, so we'll do a bit more practice for this. So I do have one more example. We'll probably start the example today, but we'll probably finish it up on Wednesday. Any question? Yes.
To the best of your ability, I don't know if you can, but what is the difference in coefficients with AC mean? Like, physically. What is that?
Ah. So the fact that we have a -3 and a -5 up here.
Yeah.
Yeah. So that basically means that, for Neumann boundary condition, there's less, I would say, emphasis on that central number. And so basically all that means is that, for Neumann boundary condition, you're not going to have as much weighting there. And so the Neumann boundary condition kind of makes it so that it's more, I would say, balanced between that and the neighboring nodes. Physically, that's a great question, actually. I don't know if I can connect it exactly to a physical, physical phenomenon. But, mathematically for a Dirichlet boundary condition, Dirichlet boundary conditions are more known to be kind of a hard condition because you're forcing the solution to have a particular value there, which mathematically is actually more tough to do. So you actually need a higher coefficient here to kind of ensure that constraint is in place. But a Neumann boundary condition is more loose because there's multiple different ways to get a derivative to kind of be the value that you want it to be. And so that's why you have less of a weighting here than the Dirichlet boundary condition. How that actually translates physically, that's actually a good question. That's probably something I'll think about and stay up late doing it while I'm feeding my son tonight. So I'll see if I can come up with something.
Yeah. Thank you.
Any other questions on this? Yes.
Since you said to keep it stable, if we say there's no like boundary condition, we're just applying it on central difference scheme. Is there instances where those liquids become unstable in an X and Y direction?
So for diffusion is a very stable process, and so we don't really have issues with stability in diffusion. Convection we do. So starting Wednesday, when we talk about convection, we run into all the stability problems we did with finite differences. And so we are going to talk about upwinding again. We're going to talk about Peclet number again. But how we actually apply the upwinding for finite volumes is actually different. But we'll kind of cross that bridge when we get there. But diffusion typically very, very stable. I guess technically it's possible to have an unsteady or unstable diffusion, but it's very, very difficult. Okay. All right. So let me do this. I don't really want to start the example in the last 8 minutes, but I do want to give you guys kind of a good thought experiment. Okay. So let's look and see what happens when we have a corner cell. So we'll expand on this thought on Wednesday, and we'll do some corner cells, right? All right, so let me go ahead and draw a typical domain again. And then let me write in some boundary conditions. So let's say we have phi is equal to 50. So Dirichlet boundary condition on the left-hand side. We have phi is equal to 25. Phi is Dirichlet boundary condition on the south side of the domain. We have a Neumann condition on the right and a Neumann condition up top too. Okay. Okay, so actually this is actually the layout of our example that we're going to start on Wednesday. Okay. Now, all the two examples that we just did, they considered cases where our cell only had one boundary condition exactly, right? So for our Dirichlet boundary condition, maybe we looked at a cell like this, right? So this here was example 1, right? Right, so we had a neighbor on the east, the north, and the south, but no neighbor on the west. Okay. And then for our second example, maybe we did a cell like this one. Right? So this right here was example 2, right? Well, I know example 2, we had a Neumann boundary condition, but same idea, right? So we had neighbors on the east, west, and north, but not on the south. So we only had to replace one. Okay. Now, technically, right? I mean, just based on the title of this section, corner cells, right? We can have cells that actually border more than one boundary condition, right? So if we look at that cell in the top right, right? We're gonna have a boundary condition on the north integral and the east integral, okay? So the question is, what do you do in these situations? Well, the way that we did these examples kind of tells you exactly what you need to do, right? It's just that instead of replacing one integral, you're going to replace two integrals. Okay. So hopefully that kind of illustrates kind of why we kind of went through, we kind of did this in kind of a very painstaking way. Just based on the four integrals across each cell, right? But hopefully you see kind of why we did it that way, because there's so many different scenarios with these finite volumes, right? Because now that we're looking at corner cells, right, you can think of even more scenarios. Like what if you're in the top right corner, the top left corner, bottom left, bottom right corner? What if you have a combination of like Dirichlet up top but a Neumann on the right, or maybe Neumann up top, Dirichlet on the right, right? And so there's too many scenarios, too many situations where I can't give you like a boxed equation like this for every single one, right? That's why it's important to kind of know this whole process so that when you do come up to situations like this, kind of exactly what you need to do, right? It does take a little bit more work than just plugging and chugging into a particular equation, but you kind of need to do this in order to get the equations correct. Okay. Now for the interior cells are easy, right? Right. So for interior cells, if you have a neighbor on every single side, you can just plug and chug. So those are no, right? But the where the boundary conditions get applied, those are when things get a little bit more complicated. Okay. Okay. Any questions on this before we wrap it up for today? All right, so when we come back on Wednesday, I have one more example to show you with just diffusion. So I don't think that'll take too long. We did most of kind of the legwork now. So we'll do practice with like an interior cell, boundary cell, and then a corner cell. And then we'll move on to convection. Right. So thank you guys for coming today. Hope you guys have a good rest of your day. And I will see you guys on Wednesday. Oh, okay, that's right. Yeah, would you guys rather take it before you leave, or but if you take it before you leave, then homework for me will not be good. So let's have you guys take it when you come back. How about the following March? How do you guys take it March? Yeah, then that way you have time to come back. How many guys are there in this class? Okay. 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 Maybe I'll have you come to my office.
Yeah, that's me.
It's only this. Yeah. So Monday.
John was like.
Yeah. So basically, right after the lecture, just come to my office. Yeah.
Yeah, careful on this host. Pay attention to the Z value. So that's how much it requests about.
Because that's the one where, well, that's the value, is it when you set it up, or is it when it's set up? And you're pretty much.
So the setup, you have a node there, I have a log. I use the half inch. So when I put